Today, we're going to get into data structures for big data. System design interviews typically aren't getting into the implementation of algorithms, but certain problems require approximations or clever approaches. Knowing about some of these data structures enables you to solve some otherwise intractable problems, and your interviewer is likely to give you points for using them appropriately. Before I dive in, I want to offer a caveat. For newer engineers, it's better to focus on doing the basics well than to, for example, pull a bloom filter into your design incorrectly or inappropriately. Aim for simplicity and solve for the bottlenecks when you can justify them, i.e., when you have those estimates, rather than solving imaginary scaling problems. With that, let's get into 3 data structures for big data. Our first data structure is the ever-popular bloom filter. Bloom filters approximate sets. If you recall, sets allow us to add items and test their membership in constant time. Bloom filters do basically the same thing. But bloom filters are dramatically more space efficient, requiring an order of magnitude or more less space than a simple hash set. This space advantage comes with a curse. Bloom filters are probabilistic, and they can't answer with the same certainty as a hash set. Specifically, bloom filters allow me to add items and they can answer in one of 2 ways. Either the item is likely in the set with some configurable probability, or the element is definitely not in the set. This sounds a little goofy, so let's build up some intuition about how this works before we dive into the system design applications. Let's pretend that we want to keep track of the names of people who have attended a meeting. If we've got infinite space, then our ideal strategy is to assign each name an identifier, maybe an index. So Albert gets 0, Brian gets 1, Christina gets 2, Zed gets 25. Then what we can have is an array of bits, which are either 0 or 1. You can think of this like Booleans. And then when Albert attends, we can change his value to 1. It's really easy for us to figure out now who's attended the meeting and who hasn't. On the other hand, if we want to save some space, we may not have all of these slots. So what can we do now? Well, maybe instead of assigning these sequential identifiers, we can hash them. We can hash their input. So we can hash Albert and take a modulo. In this case, we will modulo 4. That would give us some random value. So Albert might get 3, Brian might get 2, Christina might get 3, and Zed might get 1. What happens now? Well, when we add Albert to our set, we get 3 here. And when we add Brian to our set, we want to change the bit for 2. And when we analyze our resulting data structure, something surprising is happening here. We can say that, for instance, Zed did not attend this meeting. If Zed had attended, that bit would have been flipped. On the other hand, we can't say for sure that Christina attended the meeting because both Albert and Christina share the same value. So we've saved on space here, but we've compromised on our ability to say with certainty who is in the set. Now, in practice, a bloom filter is going to be a little bit more complicated. First, we can choose the modulo here, which governs basically how many bits are going to be required for that hash. In this case, I chose 4. I basically limited myself to 4 bits. But if I wanted less collisions, I can just add more bits. That's pretty straightforward. Another thing that I can do in order to handle collisions, and this is essential to bloom filters, is I can have multiple hashes. So instead of having just a singular hash where Albert and Christina both have the same value, I can have a second hash where now maybe Albert and Christina aren't colliding. And what this will allow me to do is distinguish the 2. Unfortunately, by having a separate hash, I also need more bits. So rather than just m bits, now I need m times k bits. The choice of m and k can actually be derived based on some formulas. They're linked in the description, but essentially what we're choosing here is the likelihood of a collision, which is also the likelihood that we are going to answer yes to a query about set membership when actually the item hasn't been added. Let's talk about situations where you might want to use a bloom filter. The first one is in a web crawler. In a web crawler, what we're going to do is we're going to be continually picking up new web pages, finding new links, basically discovering pages we haven't crawled yet, and then processing the data for the pages that we're crawling. One of the big bottlenecks of this system is this database of crawled pages that's going to be constantly queried by our workers to make sure that they're not re-crawling the same pages over and over, both to check for cycles and then also to make use of good resources. Now, if we had, for instance, 1 billion URLs in this crawled pages database, and each of these URLs was up to 1 kilobyte of data, then we've got a lot of data. Let's see, 1 billion, so mega is million, giga is billion, and then we add another 1,000. So we've got a terabyte of data, specifically just storing URLs. That's kind of a waste. So what we can do instead is we can use a Bloom filter. When workers are crawling a page, they can insert into the Bloom filter that URL. We're not going to be able to recall that URL later. The Bloom filter is only going to tell us whether we crawled it or not, but that's okay. If we recrawl a page every once in a while, probabilistically, that's not a big deal. And instead of storing a terabyte of data, maybe we store a gigabyte of data. This is a huge savings for a small performance loss on the tail end. To do the math right, mega. Another example that we can talk about is caching. Usually we put a cache in front of an expensive operation. And the goal here is both to make it quicker when we've done it before, but also to reduce the load on that expensive operation. So what often happens is the service checks the cache. If the cache has the value, we're going to go ahead and return it. If the cache doesn't have the value, we've got to go conduct that expensive operation, and then we can return that back to the user. One problem with this is it means additional latency for those instances where we miss on the cache or where we have to do the expensive operation. And this is a great place for us to potentially use a Bloom filter. As an example, if every time we insert something into the cache, we also add it to our Bloom filter, then our Bloom filter tells us whether something is likely or not to be in the cache. We can skip the cache check for those things that we know they're not going to be present and move straight to the expensive operation. Now, this doesn't work in certain circumstances. As an example, if we expect other people to be populating the cache, or if the cache has a TTL and it's evicting items. But you kind of get the gist here. We're looking for those places where a mistake is not going to be super costly, but we can benefit in the majority case where we can be mostly right with a Bloom filter. So just to summarize here, Bloom filters are a special data structure that approximate a set, and they can answer in one of two ways. Either the item might be in the set, or the item is definitely not in the set. And when it answers it might be in the set, we can configure that probability by governing how big or basically how much space the Bloom filter utilizes. There's 3 things to keep in mind, kind of 3 pitfalls that we need to be on the lookout for. First of all, you obviously need to be querying for set membership. Bloom filters aren't really going to be useful outside of that. The second thing is you need to be space constrained. Otherwise, you can just use a hash table. Memory is actually relatively cheap. A lot of use cases for a Bloom filter aren't strictly necessary anymore, but don't be sloppy. And then lastly, you need to be able to tolerate that false positive rate. If you can't actually make use of those instances where it might be in the set, you're probably better off using a different approach. Our next data structure is count min sketch. It's basically Bloom filters with integers instead of bits. The idea behind count min sketch is we basically allow ourselves to count up the number of instances or the number of times we've seen a specific item. It allows us to increment an item and then also to query the upper bound. Kind of like a Bloom filter can't tell us for sure whether an item has come through. Count min sketch can't tell us the exact number of times it's seen an item. It can only tell us the upper bound. But in a lot of cases, this can actually be pretty useful. Before we get into that, let's explain quickly how this works, and then we'll dive into some use cases. So the way that count min sketch works is very similar to the Bloom filter. We're going to have k hashes, and then for each of those hashes, we're going to have a certain modulo or width. This is basically how many integers we choose to incorporate into our data structure. This data structure is actually called the sketch, so the array of integers that we're using to store the counts. And then the count min comes from how we query it. Let's walk through an example of adding to our sketch, and then we'll talk a little bit about how we query it. So let's pretend, just like before, that Albert has added one item to our sketch. So we're going to go to our hash1 at index 3, and we're going to increment that. And we're going to look at hash2 at index 1. We're going to increment that. Now let's go ahead and add Brian. So Brian is at hash1 index 2, hash2 index 0. And let's add 2 for Christina. So Christina, hash1 index 3, and then hash2 index 2. So this is my resulting sketch after adding Albert once, Brian once, and Christina twice. How do we query this? Well, we query it much the same way that we do a Bloom filter, except what we're going to do is we're going to take the minimum value that we find at any of these hash indexes. So for example, if I wanted to find out how often Z has been added to the sketch, I'll look in hash1 at index 1, which is a 0, and hash2 at index 2, which is a 2. So I have 0 and 2. And I'm going to take the minimum of those values. So in this case, the upper bound on the number of times Z has been added to this sketch is 0, which is actually the number of times he was added. Similarly, with Christina, we're going to look at item 3 in hash1, which is 3, and index 2 in hash2, which is 2. 3 and 2, we're going to take the minimum. The minimum here is actually 2. That means that Christina has been added at most twice into the sketch. Now, there are going to be instances where we might have collisions that basically accumulate. And so it's possible that this number was actually higher than the number of times we actually added Christina to the sketch. But it will never be lower because we are always incrementing the values. And just like the Bloom filter, we can choose the width and number of hashes to basically choose a precision for our count-min sketch, or a variance on the estimate of the number of times an item has been added. A typical pattern for using count-min sketch in production is a need to keep track of the top or the highest count items in a particular set. Sometimes this is referred to as a heavy hitters problem. And the idea here is every time we get an event, an instance of something, we're going to write into the count-min sketch and then retrieve the resulting estimate for the count. We'll then update a priority queue with a list of those items. So in most cases, if this isn't the most viewed or most accessed item, that priority queue will be unchanged. If instead we are writing an item that actually is in that set, then we are going to update our priority queue. And what this allows us to do is query at any time for an estimate of those top items, but doing so in a way that is very space efficient. This queue length can be bounded by the number of things that we might want to retrieve. And the count-min sketch has a constant memory usage. It just degrades in accuracy the more we go. And so this can be used in a number of different situations. We might use it in a security context to keep track of IPs that are producing unusual traffic. We don't want to have to maintain counters for every IP, given there's only going to be a small number of IPs that are actually going to be producing those problems. We might want to keep track of viral posts that are happening on social media, where again, the tail is long, and the counts at the high end or at the head are very high. Another place that we might use this is in database query optimization, where we want to figure out what are the most common values, or maybe whether a selection criteria in a query hits something that we expect to be in many rows or few rows. And finally, you'll see this a lot in fraud and anti-scraping, where we're trying to protect against those instances where the system is being abused. And what we're going to be looking for are anomalies and instances where basically the statistics are out of whack with what we might expect from a typical user or a fraudulent user. Count-min sketch can seem really useful, but in production, you're going to find less uses for it than you might imagine because of the constraints. Obviously, we need a situation where we're counting items and querying those counts, but we also have 3 harder to satisfy constraints. First, we need to be querying against a set of known items. Count-min sketch doesn't know which items have been added, so they need to be tracked separately. In the heavy hitter example above, we track them in a priority queue. In many cases, if we need to track them separately or exhaustively, we've eliminated the memory benefit of the sketch. So we need to be careful here. The second thing is we need to be dealing with heavy space constraints. You see this in two places in interviews. Either A, your interviewer has invented an imaginary problem, like the one recently asked at Meta to build a web crawler out of Raspberry Pis. Or B, you need a constant space data structure for predictable performance, which is common in real-time systems, databases, and operating systems. Both will jump out at you if they apply. Finally, you need a situation where you can deal with the approximation. You'll see two patterns here. A, for performance optimizations, like our previous caching example, where if we're wrong, we just lose some performance. We're not delivering an incorrect answer to our users. And B, in domains where we're already outside of binary correctness. Fraud and security or machine learning and AI applications often deal with risks and probabilities and are in constant trade-offs. Countman Sketch can apply beautifully here. All told, Countman Sketch is a useful tool for your toolkit, but be careful about applying it unnecessarily. This is easily a situation where your interviewer can get a gotcha moment that you don't want. The final data structure that we're going to talk about today is HyperLogLog. I love how all these names are so fancy. And a HyperLogLog is used for cardinality estimation, or basically estimating the number of unique items. You'll see this in a bunch of different places. For instance, websites are constantly concerned with the number of unique users. This is the heart of daily active users. I don't care about the number of page views. I want to know how many people are active on my site. That is, in some sense, a cardinality problem. And HyperLogLog provides an estimation, much like Countman Sketch and Bloom filters provide estimations on their underlying. The intuition behind HyperLogLog comes from the rarity of sequences. If I'm flipping a coin, I can either get heads or tails with equal probability, 50%. If I'm flipping two coins, I've got four options. I can get heads, 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 tails, tails, heads, tails, tails. Each of those are 25% likely. If you walked past me and I told you I had gotten tails, tails 3 times, a good guess for you is that I had flipped those two coins 12 times. Now, if we were keeping track of this very rare sequence of I don't know how many coins, and I had gotten this many heads, if I walked by, or if you walked by and I had told you that I had gotten this sequence, you might guess that I had either been there for a very long time flipping many, many coins, or that I was cheating. That former interpretation is kind of at the heart of HyperLogLog. What we notice is that the more times we're flipping, the more elements we're adding, the more likely it is that I start to see these rarer sequences. Let's pretend I want to count the number of unique visitors to my site. I might have an impression stream and kind of a listing of all of the times that users have visited. And what I want to do is find the number of unique visitors, not the total number of views. And so a naive way that I might do this is every time a visit comes in, I will add that user to a hash set. And then at the end of the day, I can go and look at the size of that hash set to know the exact number of unique visitors. This works great, and it gives me a precise number, but it has two problems. One is I have to store each of my users in that hash set. It's basically a pretty large representation. And secondly, it grows unbounded. As if I have a higher number of users, a higher estimate, that means the memory of this is going to continue to grow. So how can we estimate and do this in a much more efficient way? This is where HyperLogLog comes in. So with HyperLogLog, when we get the impressions, we're going to take that username and we're going to hash it. And what we're going to try to do is keep track of the maximum number of trailing zeros in those hashes. So when Albert comes in, we see that we have 1 trailing zero. When Dan comes through, he has 0, so we don't change our number. Brian, similarly. Fred has 3, so we'll increment this to 3. Christina has 2, that doesn't change our maximum. Brian, we see Fred again, and he has 3, but that also doesn't change our maximum, which is quite convenient because Fred visiting many, many times shouldn't change our estimate of number of unique users. So what can we say if we observe a maximum of 3 trailing zeros? Well, we can come back to probability on this, but this basically gives us an estimate. We can basically assume that there was 8 unique users that were coming through. That's not a particularly accurate estimate. If you recall back, we had 5 actual unique users visiting the site, but it is an estimate, and it's the essence of how HyperLogLog works. If we kept going through this process and saw a user which had 15 zeros, our estimate gets quite large. We don't expect that to happen very often. But it also demonstrates a flaw here. If somebody just happens to have 15 zeros in their hash, we don't want to blow up our estimate just because that person happened to come through. So how can we solve that problem? The answer to this problem is we're going to do it multiple times. With HyperLogLog, we're going to maintain multiple registers, which are basically those counters or maximums of the number of trailing zeros. Let's walk through this in practice and I'll show you what this looks like. So when you write or add an item to your HyperLogLog, you're first going to hash it. And we're going to split that hash into 2 parts. The first is going to determine the bucket, or basically the partition of the HyperLogLog. And then the latter part will be used to calculate those number of trailing zeros. That bucket effectively indexes a register. So if we partition all of our ID space, we're going to maintain separate counters for all of the IDs in that bucket. And so in this particular instance, we are in bucket number 1. And at bucket number 1, we want to update our register so that it reflects our max trailing zeros of 1. Now, if you think about this partitioning, if we were to randomly do that, we would expect all of these registers to be approximately equal. And if you can imagine the freak accident where I had 15 trailing zeros in my hash, that's only going to appear in one of the registers, and it's not going to appear in the rest. So what does this look like when we read? Well, when we read, instead of just grabbing that one register and doing some math on it, we're going to take the harmonic mean of all of the registers, apply some corrections on top, and return that to the user. And this has 2 benefits. One, that freak accident hash isn't going to affect our estimate all that much, in part because it still needs to average with all the other registers, which are going to be lower. There's not going to be multiple freak accidents here. The second thing is that this averaging process allows us to smoothly interpolate. So whereas previously we can estimate powers of 2, now we can estimate any value because we have this averaging that's going on. So where does HyperLogLog show up in system design interviews? You're going to see this centered a lot around analytics workloads, where I need to determine the number of unique users or the number of unique posts that I saw. But you'll also see this in a few other places. In database systems, I can use HyperLogLog to estimate the cardinality of a column. It turns out that I may want to treat my execution differently if there's only 2 unique elements versus if there's millions of unique elements. Another place that I might see this is in cache analysis, where I want to understand from all of the incoming queries, how many are there? How many keys do I need in order to cache this effectively? The key things to keep in mind is HyperLogLog is used in those places where we're counting the number of unique items in a large data set. If your data set is small, use a hash set. There's no point in bringing in HyperLogLog. You need to have limited memory available. And the nice thing about HyperLogLog is it's bounded. You choose it in advance. But it also means that, generally speaking, if you've got more memory, you can probably use it successfully. And then the last thing, like all of our other prior data structures, we need to be able to tolerate some small estimation errors. If we're not okay with errors, we have to go with a more exact solution. All right, let's wrap things up. So we covered a lot of ground today. We talked about Bloom filters, Countman Sketch, and HyperLogLog. Bloom filters allow me to test for set membership in an approximate way that scales really well and saves space. Countman Sketch allows me to count elements in a way that similarly saves space. And HyperLogLog allows me to estimate the number of unique items in a stream of data or a large data set. All of these are going to apply in situations where either A, I have limited memory, or B, I want to make some optimizations. And things that you should be on the lookout for that might imply that you're going to use these are places where either A, your design can tolerate a bit of error or approximation, or B, you have a ton of constraints. So that interview that I mentioned earlier about having to run on Raspberry Pis or embedded systems is kind of a nod that maybe these things will apply. Now, be careful It doesn't make sense to go and bring Bloom filters or Countman Sketch in cases where the data is small, and it would actually be easier, both from a development perspective and then also from a debugging perspective, to just use a proper, precise data structure that's going to give you an exact answer. There's no need to bring in approximation unnecessarily. But in those cases where you do have some flexibility, and it's good to ask your interviewer whether you have it, these provide you a way to solve problems that are otherwise intractable. If you run an estimate and you need a hash table, and it turns out that the size of that hash table is intractable, maybe it's terabytes of data for some small part of your system, maybe you need a Bloom filter or Countman Sketch in that particular instance. I hope that this was useful. As always, leave comments if you've got questions or suggestions or, hey, Stefan, that wasn't very clear. I've also included in the links a reference to a written version of this, which goes into greater detail for our premium users of Hello Interview. That's definitely worth checking out if anything was unclear. Really enjoyed this, and until next time, talk to you then.